In this video, I'll talk about how to find out the capacitance of a cylindrical capacitor. So we have a solid cylinder here, the blue solid cylinder, which is inside a hollow cylinder, the red one. The radius of the solid cylinder is A, and the radius of the hollow cylinder is B. And we assume the charge plus Q charge is onto the inner cylinder and negative Q charge is onto the outer cylinder. And the medium between these two cylinders is air. It can be any medium, but for now we'll start with the air medium. Okay. This is the side view. Now if you look from the top view, that's how it looks like. This is the outer cylinder, and inside this is the inner cylinder. The length of the cylinder is L. As the inner cylinder has positive charge and the outer cylinder has negative charge, the electric field will start from the positive charge and terminate onto the negative charge. That means the electric field is from positive to negative, and the electric field is always perpendicular to the starting surface and also ends on the perpendicular onto the outer surface. So it is radially outward electric field. So this gives the direction of the electric field. The electric field and the dr, the displacement, are in the same direction. At each point, at all points, they are always parallel. Okay, so now first our goal is to find out the potential difference between these two cylinders. How are we going to do that? So in order to find out the potential difference, we'll use this equation, and this equation comes from the chapter electric potential. If you cannot recall it, I would suggest go back and take a look. I already have derived this equation. Okay, and A to B, what does that means? We are first finding out this E vector is the electric field at any point between the cylinder, at any point. And in order to find out the total potential, then we just integrating from this surface or this side to the outer surface of the to the outer cylinder, which is the diameter B. Okay, and again, as I mentioned, E is the electric field. Now if you look the electric field inside the solid cylinder or this cylinder, the electric field inside is 0. Okay, and why is that? You have to just use the Gauss law. If I use any Gaussian surface here, then the total charge enclosed by this surface is 0, so there is no electric field inside. And the same way, if I just look at this point, and if I imagine a Gaussian surface here, then the total charge enclosed by this surface is minus Q plus Q, which is again 0. So there is no electric field outside and there is no electric field inside the smaller cylinder or the solid cylinder. The electric field exists only between these cylinders. Okay, and that's the reason we integrating from A to B. Okay, and now we need to find out the electric field at any point here. For any point here, or let's say here, this solid cylinder just behaves like a line charge. So if you just look at here, like if I'm interested in finding out here, then to this point the entire cylinder just behaves like a line charge. So and the electric field due to a line charge is 2kL over R. But before I jump to this line, I would like to highlight one more thing here. This is a dot product or a scalar product. And then as electric field and the displacement vector are in the same direction, then these two will be simply EDR, because the cosine theta will be 0, so cosine theta will be 1. Okay, you remember that dot product A vector dot B vector is equal to AB times cosine theta. In this case, theta is 0 degree. That means E vector and dr vector are in the same direction. Okay, so we got to this state. And E is the electric field due to a line charge. And for a line charge, the electric field is 2k lambda over R. Here again, I'm introducing a new term, lambda. But if you can recall what the lambda is from the previous chapter, the lambda is the line charge density. And the electric field due to a solid cylinder or a line charge is given by 2k lambda over R. So that's how I wrote 2k over lambda over R. 2 is a constant, k is constant, and lambda is a constant. The only variable is R. And the integration of 1 over R is ln R. That's the integration of 1 over R. And the limit is from A to B. And then once you put the limit, then what you get here is ln B over A. Here I have skipped one step here. Let me write down one more step here. Ln, and first if you put this limit B, what you get is ln B minus ln A. And then ln B minus A is simply equal to B over A. Just make sure this one. Okay, if you're not understanding how do you get this ratio, then this will help you. Okay, or in general, ln or log x minus log y, if you have the 2, then you can simply write down x over y. This is the rule, this is the formula. Okay, so now so far we found out the potential difference between the two cylinders, and by definition the capacitance is defined as charge per unit the potential difference. Here I'm using the magnitude because the capacitance cannot be negative, so we're just using the magnitude here. Okay, now we can plug in the value. We just plug in the value of VV minus VA, or the potential difference, into this equation here. Okay, and lambda, as I mentioned, is the line charge density. What does the line charge density means? This means the charge per unit length. That what means the line charge density. So Q, and this VV minus VA is this value here. And here I'm plugging the value of lambda, which is charge per unit length. This charge and this charge cancels out, and the L can go to the top because this one is so here we're just dividing by L, so I can put in the numerator. So I have L 2k ln B over A. And from this relation, if I divide both sides by L, what I get is capacitance per unit length is 1 over 2k ln B over A. This is the capacitance per unit length of a cylindrical capacitor. Most of the time, the length can vary, so the best way or the proper way of defining the capacitance of a capacitor is the capacitance per unit length. Okay, that's the proper way. And then most of the time you have seen this kind of capacitor. For example, a coaxial cable. At your home, you use the biaxial cable. All around you'll see mostly the TV connection, sometimes the data transmission, they use the coaxial cable. The coaxial cable is actually a cylindrical capacitor. So that's how we find out the capacitance of a cylindrical object. Okay, and again, if you have any question, write down your questions in the comment section below, or if you have any question, let me know. I'll make another video for you. And but make sure that you subscribe the channel. Thank you so much.